Welcome to the Groundwater Lab. In today's lab, we'll review the basics of groundwater and that you did learn much of in lecture, and we'll look specifically at Cape Cod's groundwater, known as Cape Cod's sole source aquifer. There are three objectives for today's lab. First, students will be able to explain the concept of an aquifer as well as the terminology, the vocabulary connected with it. Second, students will be able to describe where our fresh water comes from here on the Cape and why we need to protect this water source. Third, students will be able to calculate a recharge area, the recharge area needed by wells pumping different amounts of water. So for this lab, you will need to have your lab manual and a writing utensil with you. And if you have access to a ruler, that would also be helpful. And I'd like you to open your lab manual to page 33. This particular lab runs from page 33 to 36. So the topic of groundwater has already been covered in lecture, but at this point in time, I want to review some of the key concepts about groundwater. So we'll go over a few of the basics on the next slide before moving on to Cape Cod's aquifer. So the first key concept is that water is abundant on Earth, but usable water is rare. So the Earth is covered, about 70% of the Earth is covered in water. So that's a significant amount of water. 97% of that 70%, though, is ocean water, which means it's salt water. And that's not water that we can drink or that most plants can take up for photosynthesis. So of all of that water there on Earth, less than 3% is actually fresh water. And of that 3%, almost more than 3/4 of it is locked in ice and glaciers. So that leaves us with only a tiny sliver of water bodies on the surface of the Earth. So these water bodies at 0.5% make up our lakes and ponds and so forth, and a very tiny percent of atmospheric water. And then we have all the below ground water, which constitutes 22% of our freshwater resources. So that's a small number, and so for that and other reasons, it does need to be protected. All right, this diagram is from your lab manual, and what it shows is the surface right here, and you can see the trees over here with some of their roots extending down into the soil. So the soil that runs from here to here has little pockets of air in between the grains of sand and gravel. And water, when it comes down in the form of rain or snow melt, will enter into the zone of aeration where these air pockets exist and displace some of those air pockets. Eventually, as it continues to trickle down through the soil, you get to an area where every single bit of air is now gone and all of the spaces in between the sands of the grains of sand is filled with water. And that's called the zone of saturation. The very upper level of the zone of saturation is the water table. So when you place a well, the well needs to go down deep enough to go into the zone of saturation. So it needs to be below the water table. So this area here, this zone of saturation, is what makes up your aquifer. So we'll take a look now at different types of aquifers that exist and look at what Cape Cod's aquifer looks like. So aquifers consist of small underground spaces within permeable layers of rock, sand, sediment, where water is found, where all of the underground spaces are now filled with water, as seen in the previous slide. There are two main types of aquifers, unconfined aquifers and confined aquifers. So ours is an unconfined aquifer. What that means is that you have the surface of the Earth here, you have the soil that is now totally saturated with water without any air spaces, and there's no rock or anything separating the soil that's in the zone of aeration with the soil that's in the zone of saturation. And like the other slide, this is showing the water table, the upper level of the zone of saturation, and it's showing you a well that's down into the water table. So the second type of aquifer is the confined aquifer. And a confined aquifer is one that has a confining layer or impermeable layer of rock. So it usually has just a very small recharge area. So only a small amount of space relative to the general size of the aquifer where the water can refill or the area will recharge the confined aquifer. And confined aquifers under a lot of pressure, so the water has been there for tens of thousands of years, and if you put a well in there, it will just start flowing to the surface because of the great pressure, and that's called an artesian well. So one thing that we want to concern ourselves with on the Cape, well, two things we want to concern ourselves on with the Cape, is that because we have an unconfined aquifer, pollutants that are introduced into the soil is going to make its way through our sandy soil very quickly and land in our unconfined aquifer. And that has happened, unfortunately. A second issue that we need to consider besides pollutants getting easily into our water is the idea of saltwater intrusion, which we'll discuss in a future slide here. But because we're a coastal area, it is possible that our unconfined aquifer, if we pump it too quickly, pump too much water out, that salt water could invade our freshwater aquifer and cause it to be no longer usable. So the next couple of slides will show you how Cape Cod's aquifer is shaped. This slide here, this diagram, shows how in many coastal areas the shape of the freshwater aquifer is in the shape of a lens. So let's start with the diagram here. You have the land surface, and then you have the saturated aquifer here, with the upper level being the water table here. Now, so even though this looks all nice and light blue, do you remember this is sand or other sediment right here? It's not water. And over here to the right, you see the ocean or the sea level there, and you see the sea floor. The sea floor is also made up of sand and other deposits. And the water likewise saturates all of the air pockets within the salt water. So you have a body of saturated salt water here, saturated sediment or sand here that's salty, and another set of soil here that is filled with fresh water. There's no, even though it shows a nice sharp line here in the interface, there's no sharp line, there's no rock separating these. Okay, it's just that the salt water is slightly, very slightly more dense than the fresh water. So the fresh water, in essence, floats on the denser salt water. And it usually forms a shape of a lens, just like a contact lens. It will continue down here and slope back upward. Okay. So the situation on Cape Cod is relatively similar. We have one aquifer. It's called a sole source aquifer because it connects the entire Cape, but it is divided into several lenses. So we'll take a look at that on the next slide. So this diagram shows Cape Cod sole source aquifer, and this is in your lab manual. And you can see that there are different depths, so it's very similar to a topographical map showing different depths. So we have a lens here, you can see another lens here, and so forth. But these lenses are in fact interconnected. So water that's polluted here mainly spends time here, but the water will move and eventually could contaminate water here. So that's why we need to pay attention and have test wells monitoring any areas that we know, any water that we know has been contaminated, whether from an oil spill or any other type of toxin getting into the water. So another point to be made here is that whether you have a town supplying your water or you have your own well, they are also all connected together. It's all the same water. In the next couple of slides and in the lab manual exercises, we'll take a look at the effect of pumping water and what effects that can have on your aquifer. So one of the effects of pumping water is called the cone of depression. That's an area where there's no longer any groundwater. So look first at the diagram on the left, and you can see there was before any wells, a water table going approximately like this. You can see that there are 3 wells here that are withdrawing or pumping water from this aquifer. And you can see that one of them is much larger than the smaller, maybe residential wells. And when these wells withdraw water, it's withdrawing the water from here. So the groundwater is now aerated and that's no longer saturated water here. If you have a well that pumps a great deal of water, it can actually cause a very much deeper cone of depression. And this area here that used to be water saturated is now just dry ground. And that is the end of these wells. These wells can no longer access water and in fact have to be replaced. So heavy pumping is a consideration depending on the depth of your wells. So in coastal areas, we not only need to be concerned about the cone of depression and making sure that our wells don't go dry by overpumping more than the area can be recharged, we also need to be concerned about the cone of ascension. So we'll take a look at that on the next slide. Okay, so first focus your attention on the diagram below. We'll get back to the words above. So here we have a coastal area and a well pumping groundwater, and you can see the cone of depression here. But remember, there was no physical barrier between the fresh water and the salt water, just an area that was different in density. But as water is pumped out of a well, not only do you get the cone of depression, you do get areas of salt water being drawn upward, if you will. So you get a cone of ascension as well. And that can cause serious problems, serious issues for coastal areas, because when the salt water intrudes upon the fresh water, it actually mixes, and that makes the fresh water no longer fresh water. It's then salty water. So next we'll take a look at the effect of pumping rates on the recharge area. So for this you will need your lab manual, page 34. So there's a table there that you'll be using, and also your lab manual, page 35. So as I said previously, the more water that's pumped, the deeper the cone of depression. So this is a diagram from your lab manual showing the original water table at the top here, and then different pumping rates. This number here, 0.5 mg per d, means 0.5 million gallons of water per day. And then the second illustration here with the deeper cone of depression shows a rate of 1.0 mgd, or 1.0 million gallons per day of water pumping. So it's pumping twice as much water and the cone gets much deeper. Okay, now take a look at Table 1 on page 35. The Table 1 caption is Area Required to Furnish Given Quantities of Groundwater. And you can see there's several columns. The first one is pumping rate. We're going to focus on the first column, which is million gallons per day. So in that column, we have a pumping at 0.2 million gallons per day, 0.4, 0.6, 0.8, and 1 million gallons per day. You can skip the gallons per minute